Welcome back. Now let's talk about some labs you can do with circuits. This is Module 2 Circuits Part B. We're going to look at labs related to resistivity and non-ideal elements. My name is John Frensley. I teach at Prosper High School in Prosper, Texas. You can like Frensley Physics on Facebook. And you know what I realized reviewing these videos? I'm a lot fatter than I remember being. I know you didn't expect me to say that just now. Now you're probably going to send me messages on Facebook. No, John, you're just big boned. Thank you very much for that. All right, something students got to be able to do in AP Physics 2. They've got to describe what resistivity is and what it depends on. It's just a property of a material, not an object, a material that describes and measures how easily, if it's low, or how difficult, if resistivity is high, charges can move. How easy or hard is it for the charge to move through the material? All right. How resistance of an object is determined by its resistivity and shape. That's your resistance equals resistivity length over area formula. Hopefully you already taught it in Physics 1. I feel like it shows up on Physics 1. I would make sure that you re-emphasize it here in Physics 2. Be able to experimentally determine the resistivity of a substance. That is what we're doing today. It has not yet shown up on the Physics 2 exam, but I'm just telling you, my spidey sense is tingling. It's coming. It's on its way. It may even be this year. Just looking at the kinds, I can just tell. I can just tell. I can use my psychic powers. We're going to teach students how to find resistivity experimentally. Specifically, we're going to want to talk about making a linear graph and from which resistivity can be calculated. Okay, adjustable spoon lab. This is a lab I do in Physics 1. You have to decide whether it's appropriate for Physics 1. We haven't seen calculating resistivity using an experiment on Physics 1. I feel like it's going to happen, but I feel like it's more likely to happen on Physics 2, of course. Here's what we want you to obtain. We want you to get a 9-volt battery. It's a cheapo one from Dollar Tree, but you can get any one you want. A voltmeter and an ammeter, or just one multimeter. You'll be measuring a voltage one time and a current on each trial. So I just have one multimeter here that I'm going to use. The ammeter must be able to measure up to 10 milliamps. The voltmeter is just for getting a precise voltage measurement on the 9-volt battery. Up to 10 volts ought to work. At least 3 alligator clips. My multimeter has the alligator clips on them, but if you've got little sticky, stabby leads on your multimeter, then you're going to need to get something that can attach to them. So that counts as 2 of my alligator clips. 2 paper clips, they cannot be coated. Obviously, they need to be bare metal so that you can make electrical contact. I don't know if the camera can see this. You'll see in a moment, these are T-shaped pins that you stick into a bulletin board. Adjustable spoon from the Dollar Tree. It looks like this. You're going to see it in a moment when we cut to the table up here. This is the adjustable spoon from Dollar Tree. It's adjustable because you can make it be 1 teaspoon, half, 1 1/2, 2, 2 1/2, 3, 3 1/2, or 4 teaspoons, and fill it with some kind of liquid or powder. That's an adjustable teaspoon from the Dollar Tree. Okay, and then I've got a beaker with some tap water in it. I just took water out of the tap. Here's the problem I'm just going to warn you. The problem I'm going to warn you is that some tap waters are very, very good resistors. So, let's see. Do I have a warning about that? Well, I'm going to come up with a warning eventually. But because some tap waters are very highly resistive compared to other tap waters, I've had bad luck with the lab I'm about to show you when I travel to another water system. In fact, speaking of which, I've never done this lab in this school before. This is my first year in this school. So how am I going to make sure that this water is conductive enough? I'm going to either put a little pinch of salt in it, or you know what, you could do this. This might offend you, but here it goes. All right, that just took some salt off my fingers. Here, let's be doubly sure. And that should be enough salt to get good results. Just in that little 250 milliliter beaker. I know that sounds offensive. You're putting water in your fingers in lab water. Come on, this is physics. This isn't chemistry. I'm not putting it into hydrofluoric acid or anything. The purpose of this lab is to measure the resistivity of tap water with a little salt in it from your fingers. And so what I said, this is the warning I gave you. Try the lab in advance with your tap water. If you get good results, good. If you don't, stick your fingers in the water, get some little salt in there to help you out. Maybe about 10 grams or whatever, a little bit of salt. Okay, to 250 milliliters. Use the voltmeter to get the voltage of the 9-volt battery precisely. So that's just going to be step one. I'm just going to get a voltage on the 9-volt battery just right now. Okay, so I'm just going to take my voltmeter. I'm just going to attach 2 little leads to it. Oops. Let's get the leads not touching each other. And I get a precise voltage. Just 9.83 is what I got just now. Don't be surprised if your 9-volt batteries are a little generous on the voltage. Just don't be surprised. All right, you're just going to get that voltage. We're going to assume that voltage is the same for the entire lab. All right, what we're going to do is we're going to set the spoon to 7 different settings for each trial. Setting for trial 1, 2, 3, 4, 5, 6, 7. We're going to try the spoon at different settings. And what we're going to do is we're going to fill the spoon with water. We're going to fill the spoon with water, and that water is going to act as a resistor. So we're going to make a circuit with 3 series elements: battery, ammeter, and the resistor that is the water. You'll see it here in a moment. So what are we going to do? We're going to measure the current on each trial. We're going to immerse the paper clips, or the pins that I have here, in the water. We're going to complete the circuit. We're going to measure the current in the circuit on each trial. And then using the voltage that we got that one time and the current on each trial, we'll get the resistance of the water on each trial. Now I know what you're thinking. You're thinking, wait a minute, Frensley, can't you just use the ohm meter setting on here? Isn't there a way you can measure resistance? Just going to tell you right now, never gotten good data using the ohm meter. I've only gotten good data using the ammeter and the known voltage of the battery in advance. So there's also a way we can get the length of the resistor. So when I fill this with water, the resistor has a certain cross-sectional area and a certain length. In order to get the length, I'm going to take the number of teaspoons and I'm going to multiply by 0.014, 1.4 centimeters basically. If you hold a ruler up to this, you'll see that each full teaspoon is separated by 1.4 centimeters. The cross-sectional area of this spoon is 0.000352 square meters. I got that by finding the volume of a teaspoon in meters cubed, and then the length of a teaspoon, and if you divide volume by length, you get the cross-sectional area. Thank you to Google for converting teaspoons to cubic meters for me. Okay, so here we go. We're going to try this lab right now, and then I'll tell you what we're going to plot.